Morning seminar. I'm Mike Cullen. I'm one of the organisers of the programme. I work at the Met Office, and you probably all noticed our spectacular, successful forecast for last night's weather. Gilbert is also working at the Met Office at the moment. He's Director of Weather Science. He's really comes from Canada, and he decided to try and run the British Met Office for a bit. He still retains his research interests as well as obviously having to spend a lot of his time going to meetings. And today you can see some of what he's been still doing research on at McGill University. So, Gilbert.
Thank you, Mike. Yes, I'm in secondment for 2 years at the Met Office, so I've done already 1 year, and I'll be around for another year, but not more than that. And so what I'll try to do today is to, as Mike pointed out, to show you a little bit of research I'm doing in the last few years. It will span probably a decade of work with different PhD students at McGill University, and which have always a relation to numerical weather prediction. So what I'll try to do is give you an idea where numerical weather prediction came through the last 10 years in terms of hurricane prediction to what we can do as best now and what could be ahead of us in 5-10 years from now. All this at the same time with a topic which is of interest to me is to look how hurricanes evolve and what drives their evolution, especially for the intensity. In the last few years, we've done quite well in predicting storm track the track of the storm, and what is still a challenge is to be able to predict the intensity, how well an hurricane will be intense, and that will be the main topic of the discussion today. And I will use some tool to take a look at it. And you'll see, and it's nice, 20 years ago I was around here as a postdoc working with Peter Haynes. And a lot at that time was about wave process, wave breaking, how we can explain mean flow wave interaction. And you'll see, and this was done in terms of a global stratospheric dynamics. You'll see here the same sort of idea can apply to the vortex which formed the hurricane. So that will be my talk. It will be split in, as I said, some motivation coming from numerical weather prediction. By the way, if people are interested in climate, it will tell you a lot also how much climate model can resolve and explain the intensity of a hurricane. And you see that the challenge is still quite bigger for climate models, which are run at coarser resolution. But I'll give you a good motivation on this along the way. And we'll take a look, as I said, at the hurricane intensity. We'll use a technical empirical normal mode analysis. I will present this in a quick manner, but we'll give you a flavor, and probably the only real mathematics I'll show, quite basic, but you'll see how powerful the tool is. And then I'll use that tool to take a look at unstable vortex, which are linked to a problem in hurricane dynamics. And also I'll show you diagnostics of a full 3D hurricane and explain you how the Vortex Rossby wave and hurricane, to make it simple, they are really the spiral band you see normally around an hurricane. And the question is, of course, it is important because the spiral band our region of high precipitation, but do they play an important role in terms of dynamics? That's what I'll show you, the importance of those spiral band, which we call here, in this case, Vortex Rossby wave. So that's the plan. Climatology, I think I can have a pointer here. That's a challenge. It's really a North American phenomena. I know that some newspaper were announcing a hurricane hitting England yesterday, but that's not possible. It's impossible. In fact, there's no historical remembrance of a hurricane hitting this region of Europe. But clearly this is an important topic for North America and even Canada, where you can have sometimes re-intensification of hurricane as they go northward for different reasons. I'll point out two along the talk. So what I'll show you is what is a state-of-the-art model in global forecasting and how it represents very well or not a hurricane. Just with one example, and then we'll go more into detail of the dynamics of such a vortex. So that was 10 years ago, and that's a good example. This is the Canadian model, but other models would have shown the same thing. This is a 5-day forecast, global forecast, and what we're showing in color is precipitation, essentially. At that time, numerical weather prediction model had a resolution horizontal, which were around 100 kilometer resolution. And the time step on those models was 45 minutes. What I would like to point out, since the topic is about a hurricane, tropical cyclone, or typhoon, depending where they are, there is a tropical cyclone developing here just beside Madagascar. And this animation, it's not obvious that there is something going on there, except there's some rain. All what is red is like this storm here and the storm track here. All is red is intense extreme event. That was not clear. It was a cyclone, but certainly not a clearly developed tropical cyclone with a spiral band. What I'll show you is that in 2003, a new version of this model was put in place, and you had now we'll get a time step of 15 minutes and 1/3 of that resolution, 33 kilometer resolution, and you'll see the difference. So now you clearly see that the storm, let's say on the Atlantic, are more well developed. Fine scale are obvious here, some shearing here, and that you can start seeing this tropical cyclone with the spiral band around. So at that time, our global model at those type of resolution were just starting to resolve properly those spiral band. I'll just give you a zoom on this one. This was a well-known catalogue cyclone called Dinah, and see you have the Madagascar Island. That was a track of it. Now just showing you again those two cases. That was the low resolution version of it for a few 1 day, 2 hour day. So clearly you don't see those spiral band developing, and we'll clearly understand that in the next few slides. And that will be the high resolution version of it. So it's starting. It's not there, but it's starting to do it. Now, of course, the question was, those spiral band, what role they playing in those tropical cyclone or hurricane? And see, it wants to start doing them, but not really there. So let's talk a little bit more about those spiral band or Vortex Rossby Wave. The end of the 90s, Montgomery and Kallenbach point out that the Vortex Rossby Wave, those spiral band, could play an important role when they propagate outward from the main vortex. At the same time, it permits to have angular momentum to build up close to the eye wall, and that helped to spin up the hurricane. That was based on experiment and some classic techniques like Overmøller diagram, etc., etc. Other things which seem to be clear about instability in hurricane, you don't see it, I'll just put a zoom. There is Vortex Rossby waves seem to be able to be explained with instabilities. Unstable. If you look at the basic state, it is barotopically unstable and can spin up a hurricane. And that's a zoom on this part, and you can clearly see this instability, which in the work with Schubert was looked at with a simple model. So clearly see here the structure here, or an unstable mode developing with a wave 4-5. So that's a two mechanism that seems to be quite fashionable at the end of the 90s to make to spin an hurricane and intensify it. So at that time, It's probably when I started looking at this problem myself with some of my students at McGill. So the question was, can we characterize and quantify the dynamic and significance of the spiral band? And studies have shown that the spiral band has characteristics of vortex Rossby wave. And one of the difficulties in this problem is that the Rossby number is not small at all. So there's no natural separation in frequency between gravity waves and the Rossby wave, the vortex Rossby wave. So it's difficult to say this is a gravity wave and this is a vortex Rossby wave. So there are mixed, and it was even, and it's still even, I would say, scientists, but it's quite a minority now, that feel that those vortex Rossby wave are gravity wave in nature, and they're a characteristic, which I'll show you is not the case at all. So we use a method to look at this problem, and I will introduce that to you, the empirical normal mode. And this was done in 2003, a paper with Chen, one student that was at McGill and now a professor at York University and Toronto region. So essentially what we'll do, it's a principal component analysis of the variance around the vortex for those Rossby wave, vortex Rossby wave. What will help us is but the new aspect to it is that when you do an empirical orthogonal function and you construct this, you need to develop a metric. You need to have a bilinear form, and that's always been arbitrary what you look at. You can look at potential vortices, you can look at a lot of things, and this approach, you take the wave activity, which are conserved quadratic invariant of the equation, of the linearized equation, to the basic state you have. And you'll see in this case, it is quite powerful because it links the EOF to the normal mode of that system. So I'll show that in the next few slides. And this was used in different problems for planetary wave, gravity waves, and for those vortex Rossby wave in hurricane here. That's a series of papers on this topic. So first we need to derive the wave activity. That will be used to do a principal component analysis. We use the hydrostatic primitive equation in storm following isotropic coordinates, so we follow the hurricane. We'll assume a small amplitude perturbation. The basic state that we'll use is the time azimuthal mean, and the azimuthal invariant is linked to the pseudo momentum, and the time invariant is known under the pseudo energy density conservation. So you have two invariant to the linear equation, and then what you'll do essentially is to use it to do a principal component analysis. Why doing that? Well, it has very nice properties, and I'll show it to you after I just introduce them. So that's the conservation law for the pseudo momentum. The pseudo momentum itself is this quantity, this two term. One is vertical, that's the potential vorticity disturbance square, and these quantities just depend simply on the basic state. They are fixed along the problem. This term here is essentially, if you take it in terms of shallow water model or density here in the isotropic coordinate, density perturbation multiplying the wind perturbation. This term is linked to gravity wave, essentially. You can see that gravity wave will contribute to this, but the vertical mode will just contribute to that one here. That gamma is a very important one. This is the potential vorticity main gradient, latitudinal, well, not latitudinal here, but radial gradient. So it's really the restoring force mechanism for those Rossby wave here. I'll show you a picture of that, so you'll have a better view on it. What is nice also is that once you have this quantity, and you will use those bilinear form to calculate the EOF in this problem, then you can look also at those flux term here. Essentially, this one is very interesting. It gives you the inward momentum, or momentum inside the vortex or outside, and we'll look at them for each mode. And we have here the term which is linked to the heat transport and the horizontal.
So is gamma going to be one sign?
It can be two signed. I'll show you example where you will have the possibility to have an unstable mode, and you'll see clearly a pair of counter-propagating vortex Rossby wave combined together, creating an instability. So
But you will be able to deal with that in your wave activity.
yeah,
Yeah.
I'll show it to you. So that's a pseudo energy. You understand why you need those two? Because it's quite powerful. Once you calculate those two quantities, you can do a lot with it. That's a pseudo energy. Essentially, if the basic state was the basic state at rest, this will be a total energy. By the way, the pseudo momentum, if the basic state was at rest, it would be simply entropy. But the fact they are shared wave, you need to use those things here. So the pseudo energy is a kinetic term, disturbance of the square of the disturbance of the wind. That's a potential available energy, and that's what I call a Doppler shift term. Essentially, it's essentially, you can show it's really the Doppler shift of the mode. Now, I think that so how we calculate those things? Well, we proceed in the following manner. So a principal component analysis telling you essentially that the function that you want to expand in time and space can be decomposed on pattern or special pattern with the principal component in front, with depend on time only, and you have a residue. That's the principal component analysis. When you do an UF analysis, this guarantees you that the first mode, which explains the most variance, is the first one you'll find, and the second is orthogonal with explaining as much the variance then, and she just rank 2 and 3, 4, and then you can reconstruct completely the signal that you want to look at. How you calculate those functions here? Well, here we use, there's two ways to do it, but in this talk, what essentially we do, we calculate the covariance metric in time with different time. And the covariance is simply calculated by using this function, and you average in space. And then you estimate those covariance at two different times. So it's like a metric. I'll show what B is afterward. Normally for an EOF analysis, B is the identity. Okay, so we just put 1 here. So once you have calculated this matrix C with different time, you calculate the eigenvectors, and then you get what we call the principal component. They are orthogonal between themselves, which means they correlated in time. And you can take one principal component, reproject it on the series here to get the space pattern. And that's the UF. UF 1, 2, 3, 4. What is new here is that B is not the identity. It is a metric, such a manner that this product here is the pseudo-momentum or the pseudo-energy. In this case, for pseudo-momentum is almost trivial. You have here this gamma function, as we have just discussed, and you have those two terms, which will reconstruct essentially the expression I've shown you at the beginning. So that's a recipe. There's nothing more to do to interpret physically what you obtain from those analyses. One important thing to say on that, before we go showing you some result, is that when you have a subscript here, it means you have integrated the total value of the space pattern. Okay, so the pseudo energy total for one mode normalized by the pseudo momentum with a minus in front, well, essentially equal the phase speed of that mode. And so what you can show quite easily, in fact, when you do it, well, you try it a few different manner, but at one point there's a neat way to show that. What you can show is that if you have a linear system which is stochastically forced, with shear wave in it, and you have a stochastic term forcing it, you can show that when you do this analysis, the principal component analysis and the UF you obtain are the normal mode of the system, which means, if there was no stochastic forcing and just have a linear system, this will be the normal mode with a pure oscillation pattern. This formula is essentially the equivalent, let's say, of the pendulum formula. If you have a pendulum of a length L, I can tell you this natural period of oscillation. Well, that's the same thing here for the normal mode, except we have an infinite of them, and they are nonlinearly coupled or forced by stochastic noise. One nice result is that this formula, the phase speed work very well if the system is non-forced. It's a free linear system. But what you can show also is that if the stochastic noise is really random, as it should be, then you can show that this formula is giving you essentially the centroid of the power spectrum that you'll obtain for each of those principal components. So in other words, in place of when it's forced stochastically, you will look at the power spectrum. You won't get a pure oscillation, a delta of Dirac, but you'll get a red spectrum sometime in the atmosphere. You'll see what you'll get here with the hurricane, but it's not a pure oscillation. But the centroid of that power spectrum is always given by this formula. And this has been used in different contexts for planetary waves, gravity waves, all sort of other problems. It works each time. You can do it with a controlled numerical experiment also. So that's when you're starting to be able to have a physical interpretation of those EUF. That's one thing which always be how you could criticize the EUF analysis is that they don't have really a physical interpretation. In this case, it has one. So, just to conclude on that one before I show you some results, essentially, the empirical normal mode theory bridge two important diagnostic tools for geophysical fluid dynamics studies, principal component analysis in normal mode theory. It permits you to make the connection between the two. Okay, let's apply it to a full developed hurricane. So you need to put all your data. This is a model simulation. I'll show you. You cannot do that with the real world. You don't have enough observation, but it's ideal to look at a 3D model or 2D model when you have all the data. Well, you can do this sort of analysis also for planetary wave using analysis, which is a combination of model output and observation. But in this case, it's just model that we're looking at. So you go in isotropic coordinate, you remove the basic state, in this case time azimuthal mean. You do an azimuthal decomposition, so you look at wave 1, wave 2, wave 3, wave 4. So you do that independently. And you find those empirical normal mode, time series and spatial pattern, and then we'll discuss the kinematics and the dynamics of each of these modes. So how this works? Well, you have those maps. This is PV at 0 hour, 6, 12, 18. So, but you have a time sampling here to do this analysis of 2 minutes. You have a map each 2 minutes for 24 hours. So you can build some statistics here. That's the basic state. That's a potential vorticity profile. You'll see that oftenly, those type of graphics, so I'll explain you them. This is the isentropic coordinate, this is the vertical, and this is the radius from the center of the hurricane. It's a following coordinate model. And here, this is radius 120 to 340. That's a profile of potential vorticity. Not too much here, a lot in the middle here. So that's what you would expect to see waves being on the region where there's a strong PV gradient, and that's the PV gradient, that's the function gamma. In this case, here you have a negative value and a positive value. In that problem specifically, as you see, there is a reversal of sign of the function gamma, which means in linear stability theory would indicate a possibility to have an unstable mode develop there. It won't be the case here. I'll explain you why. But afterward, I'll show you a 2D problem where you can see that sort of unstable mode developing. Then you calculate those empirical normal mode. That's a spectrum. ENM1, 10, 100 to 1000 almost. That's a spectrum of the pseudo momentum and the pseudo energy. That's negative value. Essentially, this one retrograde and this one prograde around, which I mean by that is that if you take just this term here, okay, this is positive definite, the pseudo momentum can be negative or positive. This will mean that the retrograde or prograde around the vortex. That's a Doppler shift term here. Yeah. So there's no unstable mode in this case because it was shown by Wren in 2003 that when the wind profile is monotonic, it stabilizes the flow. And it is the case here. I'll show you a case where it's not like that later. So you have all those modes which are orthogonal using the pseudo momentum, and then you start trying to interpret what they're doing there, the dynamics. First, you can split the spectrum and this what I call the gravity wave term and the vortical term. As you can see in red here, this is the vortical contribution and this is the gravity wave term. It's quite smaller. This is a logarithmic scale, right? So it means that essentially those waves that you see are the vortical wave or Vortex Rossby wave. The gravity wave doesn't seem to play an important role. I'll explain you later what the gravity wave do in this problem, essentially. That was for wave number 1, and this was for wave number 2. So the spiral band, if you reproject that on the data and look at wave 1, the first mode, then you see a real clean Vortex Rossby wave propagating or retrograding around the vortex. An example, we'll just look at one. The wave number 2, it's a pair. We have the time series, you can look at it. It's not a pure oscillation, of course, but you can see they are in quadrature. You can look at the power spectrum of the 2 mode. There's a peak at 1 hour, and this formula for the phase speed, the natural frequency of that mode, is 1.1. So they correspond, telling you that that's certainly a good start to having a Vortex Rossby wave when the 2 time series on quadrature, and the peak of the power spectrum is at the same place that you would expect for that mode. You can look also the polarization. In other words, you can always develop a Rossby wave or a wave and imaginary part and real part, and you have 2 structures. You get 4 structure pattern here in this problem, and you have a polarization formula. You should have positive, the same value here, and here the same, but with a minus sign. You look at them. That's an example for this one. And clearly, you have your 4 vertical profile here with radius, and there's 4 pattern there, and they have the correct polarization for being a Vortex Rossby wave. You can split this. That's a nice way to show what's going on globally here. This is the frequency, and this is the mode number, ENM mode number, and this is the maximum wind here. Essentially, you can distribute them, and that's the distribution you get essentially. The part under is related to a continuous spectrum. It projects on the continuous spectrum, and it would expect as all the properties of continuous mode. This part is a discrete spectrum, and these are the gravity wave. They don't have a lot of contribution, and by projecting those discrete spectrum on the data, what you can see essentially is at the start of the integration of that hurricane, you see them propagating gravity wave outside of the vortex. And then essentially they represent some emission of gravity wave linked to the vortex, which wobble a little bit and all that, but they don't represent a lot of variance. So you need to focus on the first one here. Now, of course, that summarizes a little bit what I just said. So we have those maps. This is the wave number 1, 2. The main result. In this table, you have all the modes which explain almost 50% of the variance in that simulation, which is the nonlinear simulation. I'm using a linear dynastic approach, but I'm looking at a nonlinear full-fledged integration here. And what you have, this is the first pair with a period of 2.4 hours with variance 11.8. You have another pair there, that's the propagating one in this problem, with a period of 1.6. Wave number 2 with period of 1 hour. These are the waves which are explaining the most variance you see. Then I think I can come back what I've shown you at the beginning of my discussion. I've shown you an integration of a model at 100 kilometers with a time step of 45 minutes. And there was no Rossby wave there, Vortex Rossby wave. At 30 kilometer resolution and 15-minute time step, you should start being able to capture such things because those Vortex Rossby wave has a typical period of 1 hour or less. So you're starting to resolve them at those resolution. It's why you didn't see them before. Now, all this nice, it's important for precipitation, but do they play an important role in terms of dynamics? That, I will argue that now, that they are important in fact. Remember, I've shown you the conservation law for the pseudo momentum, and I have flux term. So what I'll show you is a divergence of those flux term, which we call, and if we average around the along a circle, then are the equivalent of the Eliason-Pound flux, and it can help. You can relate it to this equation here. Those two terms are negligible. Essentially, it's giving you how strongly they are interacting with the mean flow and able to accelerate the vortex. And what you look at the numbers, well, what you see is that those, the one I've shown you, okay, here is an example. This is a wave 1, the first mode, 2 mode. That's a contribution. This is radius again. This is the vertical coordinate. Then you see an acceleration just inside this line here. That's the critical line of that mode. Critical line meaning the phase speed match the wind speed. Okay. Yes.
Sorry, the effect is accelerating the
Yeah.
hurricane there.
Yes.
Where you have the red color.
Yeah. That's accelerating, and this is decelerating.
So you're accelerating near surface.
Yes. In this case, for this problem, so it's right on here. So essentially, this mode is contributing a lot to the acceleration, low and middle troposphere, inside, outside the eye wall, and it decelerates upper troposphere in the eye wall. Okay, just up there. The wave 2, the same sort of thing. It has a critical layer signature, okay, in the sense that the phase speed of that mode seems to be the place something is going on. Now, 2 meters per second per hour, when those things goes for 24 hours, 48 hours, it is important. It's significant. It's playing a role in terms of accelerating or decelerating and contracting the eye wall. I'll show you some example of that. So that was, I took some time here to explain you what this was doing. I'll just go a few results of hurricane dynamic, which, as I said, I've done with a PhD student at McGill. Now, that one is an instability, and you would like to be able to represent an unstable mode, which will be different what I've just shown you. So to do it, it's we do the experiment of Schubert in '99. It's a vorticity ring. It is an unstable ring of vorticity. This is a 2D problem here, okay? And, well, that's it. Can trust me, this was well done. The basic state, here you have the azimuthal wind. Essentially W omega O is here. That's the maximum of the jet here around the vortex. And if you look at the vorticity, that's a profile of vorticity, and this is the gradient of the vorticity. And you see a clear change of sign minus and plus here. So we'll analyze this one. That's the integration of this model at 3 hours, 4 hours. So you see it's evolving. It's an nonlinear model, of course. Then, same business as usual. We'll look at the spectrum. We'll look at the EP flux. So what we have here is the spectrum. A pair here, up there, really important. There's something going on here. Those one are the prograde. This is the retrograde mode. Only the vertical term is contributing into the pseudo-momentum. It's a barotropic, it's a 2D barotropic model. There's no gravity wave here, of course. And an unstable mode may arise because I've shown you the gamma change sign. So that's the time series for the two extremes, the one with retrograde and prograde. So they are counter-propagating, and those two pair, and you see clear exponential growth at the beginning of the integration. You look at the complex pattern of the mode. It has a nice, what you would expect, polarization signature. The same for the second one, which was in this case prograding. And you look at the total of those two. They're counter-propagating, propagating, and combined together, you can check. They have a total pseudo-momentum of 0, which that's a condition for an unstable mode, because you cannot conserve a quantity if it's non-null at the same time be an unstable mode. It's a contradiction. So it has to have a pseudo-momentum of a value, a total one of 0, to be able to represent an unstable mode. And it is the case here. And what essentially it's doing here, those propagating, counter-propagating modes are simply decelerating. This is the high wall, and accelerating here is simply contracting the vortex and spinning up and getting stronger winds. With the same technique, you can look at problem where there's quasi-mode also, quasi-mode that we use in plasma physics. It's quite, in that sense, quite powerful to extract the relevant process going on in this sort of a problem. So that's a sort of summary of this vortex ring. I won't insist too much on it, but it has, in this case, it has period, which was quite similar for all the two pair. What you need to have a phase locking, and the variance. Yeah. Last, but not the least, important problem in hurricane prediction is that 70% of them do something which is called high wall replacement cycle. And I'll explain you this with this graphic here. Essentially, what's happening is that this radius is the middle here, okay? And that's the first 12 September forecast to the 15th of September. And that's the wind profile. So you see here the high wall here, and you have a spinning hurricane. And what you see is that eventually, and that's the outer red line here, you see the buildup of another peak in the maximum in the wind, and it slows in and eventually replace the other jet around the vortex. And we call that high wall replacement cycle. It can take 1-2 days. It's a slow process compared to the oscillation of those waves. Those Vortex Rossby Waves, which have a period of 1 hour, 2 hours and less. And they are very important because, example, Katrina, when it hit New Orleans, it was in a down size of a high wall replacement cycle. So it could have been worse, but it was not at its maximum strength. Sandy, who hit New York last year, was it was a sort of scenario where this was getting stronger and stronger because there was another cycle of re-strengthening. At least some simulations seem to show that. I didn't do the Sandy case, but looking at the vortex profile, you could see there's something going on there. So to look at this problem, that's the last problem I'll show you today, was to do the same analysis and look at the EP flux and see if again those Vortex Rossby Waves play a role in spinning up and replacing the high wall. So we have done an experiment with a full 3D model from the GFD-L, and there was different type of resolution utilized with different physics, but it's not very relevant for the discussion today. That was a domain of integration. What I'll show you is a result coming from this green square here. We have doing a simulation of the hurricane at very high resolution in the core. So that was the track, I think, in black here, and that's the simulation. Didn't really follow well. I'll come back to that. Predicting a track of hurricane is very sensitive to initial condition. It's very difficult when just one case to be able to get right the track. But the deepening and the structure is normally well retained here. That's the central sea level pressure. That's the analysis, and this is the model here in gray. So the evolution was relatively well captured there. So that's a simulated reflexivity. In other words, what a radar would see of that hurricane that we're simulating at different time. That's the profile. As you can see here, that's the first initial condition, the profile of the wind. So just one jet. The second one is this gray here. You see there's a second jet developing, another one here, another maximum here. So you have a cycle there, a replacement. It going inward. Now if you look at the picture, you can see there's something trying to see, that's the eye wall, that's inside the hurricane, but this guy here is slowly developing, okay? You look at the Sandy one, we hit New York, you can see at the last 1, 2, 3 hours before it hit the coast, you can see something like that simply coming back. Just by looking now at it, it's almost obvious. So that's the angular velocity for this problem. This is the potential vorticity. So again, in the vertical isotropic coordinate, the radius 0 to 80 kilometers here. That's a potential vorticity, and again, you have a possibility, a reversal of sign in the PV gradient, so you could have an instability here. That's not really what we want to look at now today. The same business as usual. You get the spectrum, you get something which all the Vortex Rossby Wave get a good contribution from the rotational component, and gravity wave not so important. Again, the phase speed, and next step is to look at the Eliason bound flux. But first, that's the power spectrum of the most important mode that you have in that simulation, and that's the peak. That's the polarization relationship between the 4 maps. It's doing well, and it's a retrograde vortex Rossby wave in this case. What is interesting about it is that its EP flux divergence show at the critical line further away from the eye wall. Again, this critical line type of signature, it's contributing to the acceleration of that second. That mode is able to bring that second jet maximum of wind. And that's just give an example, a period where there was nothing going on and you don't see anything there. But that's inside the hurricane here. So this mode was really playing a role in accelerating the second maximum. You can look at AP flux also of Malloy diagram, which you could do, and you can see the Malloy diagram. Here, this is the radius. This is time. You can see that mode essentially is responsible for that part that you see here. So it's accelerating this second maximum. So, well, first thing, it was not obvious 10 years ago, and I have to say, it is not for everyone obvious, but if there's something to conclude from this, is that if you want to predict very well intensity, and this turned out to only be important for very powerful hurricane, category 3, 4, 5Y, because in the case when the hurricane is of category 1 or 2, the vortex Rossby wave, the period are quite long, and the critical line is far away, and they don't play an important role in building up the hurricane. Only when the hurricane gets really strong that those Vortex Rossby waves seem to have a critical line close enough to play an important role in spinning them and redistributing angular momentum. But in our case, if you look at some experiment at high resolution, numerical convergence for those Vortex Rossby wave and the momentum start being quite reasonable at 1 kilometer resolution. So that's the message to take home here is that if you want to look at extreme event, let's say in climate model, which presently have resolution of the order of 20, 30 at most, or even more close to 50 kilometer resolution, you won't be able to answer a question about the how much, let's say, a hurricane statistic would change in a climate change scenario, because you cannot really, for the most extreme one, have a proper representation of the mechanisms, the dynamical mechanisms that permit them to spin up. Different case we've done, and I'll show you, give you the reference after that, seem to show that those critical line layer problems seem to be quite relevant for what's happening in a hurricane. Like it was used years ago for stratospheric wave breaking and mean flow and wave interaction. This seemed to play an important role. One challenge is interesting is this one with the IOR replacement cycle, because the critical line in a way is moving inward at a very slower time than the oscillation itself. There's a separation on time scale here, but it would be a nice problem to see how this works. Maybe it could help us have a better understanding what's going on there and what control those formation of IOR replacement cycle. It would be a nice critical problem, but with the critical line moving inward as the mean flow is spinning up. So that's the reference. I think I saw a card here asking me to give you the presentation, so you can access the 4 papers who certainly dealt with this problem. I've shown it to you today. And what I'll do, I just have a few minutes to do it. I'll show you where we are in predicting numerical weather prediction, with numerical weather prediction to predict hurricanes, and probably show you also what we could do probably in 5-10 years from now. And on this, I'll stop. I'll do the prediction of the problem of predicting Sandy. So that was quite an event, of course, with a lot of damage and impact over the East Coast, showing you how some great cities like New York are not even prepared for such thing. And would like also to point out that in terms of numerical weather prediction, it was quite a success, because the first global ensemble were predicting the occurrence of Sandy were already flagging that at 7 days in advance, that this was coming. The European Center was the first one, the European Center in Reading, and at the Met Office also, even after 7 days, we could see that something was coming. So 7 days before US landfall, the strong probability of US landfall was flagged by the MOGREP is an acronym, I should have spelled it out. It is the Met Office Ensemble Prediction System. As you know, I'll show you an example just after that. It's very difficult to predict an hurricane track. It's very sensitive to the type of observation you're using, initial condition. So what you do, you run 100 different models, and you can construct a probability distribution function of the track, and that's what you see here. At 7 days in advance, that's the track in black here. That's the East Coast. You could see where was a little bit to the north where it effectively landed. And that was the strike probability. This was the track, essentially the track that they were looking at. There was a one few there going completely to the right hand side there. That was at 4 days. Then it was already predicting very well. And all the other centers in the world were showing that. If you think in the 30s, 20s, 30s, when there was no numerical weather prediction and neither satellite to see them arrive, the call was maybe 12 hours. You could imagine, when you look at the statistic of death with a hurricane in the 2030s, it was awful. On the coast, hitting a city with no warning, the result was incredible. You know, they could prepare this time with that sort of forecast. Here, the highest resolution model that the Met Office could run last year was a 4-kilometer resolution. So it tells you a little bit that 4 kilometer, it's starting to resolve very well with Vortex Rossby Waves. The density was not was quite okay also. So as you see it propagate along the coast. Something unique about Sandy also, it's the first hurricane in history to just take a left turn with no reason. This is the first time something like that happened. It's still, I'm not sure to understand very well why, or at least I don't have the knowledge that to explain why in this case, especially this case, it went simply to the left, to the west there. That's when it hit. So that's what we have for hurricane prediction at 4 kilometers. I think the spiral band and all that are very well resolved. It turned out that also I've done a problem. I like to show it, even it was done in 2000, at the beginning of 2000. It was a collaboration with Japan on the Earl hurricane, which started here and make an incredible spin up, what we call extratropical re-intensification, just there. In that case, it was mostly because it was interacting with the polar vortex and was able to spin up essentially by this dynamical interaction. And what was interesting with this problem is that we had access to the Earth simulator in Japan, which is still a numerical simulation which is unprecedented. There's no one who has done something so big. Even if the computer is still improving in capacity and capability, that Earth simulator was a supercomputer that still one of the best we've seen in the last 10 years. And essentially what I'll show you is, as I talk, I'll show you the domain of the integration here. That's vorticity of this simulation of Earl at 950 hectopascal. And that's Earl there. And this was a preliminary run done at 10 kilometer resolution. You'll see it spin up. We need to redo at 2 times one there and another time here. Reinitialize the hurricane because it was going somewhere we didn't want them. We didn't want the hurricane to go. And again, because it's very sensitive to initial condition. So to have a full cycle, we had to, and you'll see the animation will jump a little bit. As you'll see this one here, it will interact. You'll see it's quite impressive, and all the large scale that you'll see associated to it. So it's there now. Another reason we can re-intensify hurricane is less dynamical. Sometimes the Gulf Stream here has patch of warm water, and if the hurricane in transition just hit this warm patch, it re-intensifies. Like happened with U1 who hit Halifax a few years ago. Now take a look at this one. This is quite impressive. That's it. We have reinitialized it, and you see it's quite a large scale feature. It's quite a. So that was a 10 kilometer to prepare the integration on the Earth simulator. On the Earth simulator, we have the same domain, but 1 kilometer resolution by 100 kilometers, 10,000 point by 10,000 point, with 80 levels in the vertical. And that will be the last animation I'll show you. Of course, I cannot show you all these domains. I'll just show you the Gulf of Mexico, which represents 1% of the tile that we use to integrate the system. And you see Earl spinning up over the Gulf of Mexico. That will be probably done globally. The European Center expect to have a 2.5 kilometer resolution model in 2020. So 2030 is probably what we would get. But of course, this is not a global run, but it was quite an important run. As you see, this is a simulation of humidity at 350 meters. So I think with this, I've tried to show you a little bit where we were in terms of numerical prediction with the hurricane. One aspect of it, the dynamical process inside the vortex, and the role that those spiral band can play and what it needs to be able to resolve them properly. So on this, I'll close my talk and can answer questions if you want.
When you, at the beginning, when you show the pattern of intensification of, of basically push of the angular momentum, so I guess, correct me if I'm wrong, so these waves tend to accelerate the hurricane near surface, right?
Yeah.
So I expect this is exactly the positive feedback you need, because you needed to push up more water, otherwise you
Yeah.
get killed.
No, of course.
So I mean, there is the energetics behind it, otherwise
Yeah.
it's like it's
They're
like
pumping
an
moisture and the diabatic release in the spiral band. It turned out that the precipitation is having the same structure than those Vortex Rossby Waves. So
Yeah.
you can see them projecting very well on those source term,
Yeah,
and
yeah.
which maintain them against drag and all that. And but there seem to be a redistribution of angular momentum, which is that's what the Vortex Rossby Wave do by redistributing angular momentum. So that's I would say sort of a second order effect. The first order effect is well explained by Kerry Emanuel. It's really the thermodynamics which pumping those vortex and the release of the adiabatic heating to the precipitation process.
But you have anyway some sort of negative viscosity effect.
Yeah.
Because you're putting angular momentum where there is already a lot.
Yeah.
So there must be an energetics behind that supports
Yeah.
this. Otherwise everything would
Yeah.
die.
Yeah. Yeah. Of course. David?
Yeah, you used isentropic coordinates. Were there any, well, two questions, I guess. One was, does that present any technical problems due to the fact that the bottom's not an isentrope necessarily? And then are there any of these modes that are surface trapped in the kind of, by analogy with surface quality geostrophy or something like that, that are driven more by the
Yeah.
surface temperature than by the potential vorticity?
That's a tough question. Go with the second one and I'll tell you.
Okay.
Oh, you have a note?
No, that's
Okay, that's it. Well, okay.
Yeah.
Yes, in this problem, we assume that we're forced by the system is forced by the surface, and of course you can have isotropic coordinate that cut
Yeah.
the surface, and that you can do it with this problem.
Okay.
One difficulty is that when you do that, there is contribution from the ground, of course.
Right.
For planetary wave, we know very well the baroclinic life cycle have to have an interaction with the surface. You can do this problem. I have to admit, when I've done that in '94 for the planetary wave and also with Ertanzadra in the 2000 on planetary wave, we simply assumed that the boundary layer was a sort of forcing stochastically those modes, because we had a lot of difficulty to deal with those terms.
Okay.
The good news on this is that John Midvin at Reading University of Reading, was able to deal with this problem now. And we have redo some calculation where we take account of the surface process in this analysis, and it seems to work very well now. So we are redoing some of those calculations. For the hurricane, it comes out that we think also it could be useful to see how the surface is dealt properly. So in those problems, we're just assuming that the boundary condition at the surface was stochastically forcing those waves, and it was source of moisture and all that. But we didn't really try to deal how those waves interact with the surface, because it's hiding on areas was difficult. At first approximation, it seemed to show a lot of insight in the problem, but the surface need to be looked more closely.
But and then you showed this example of the acceleration being sort of near the surface.
Yeah. Well, surface have to be careful.
Well, not the bottom, but I mean it was the
It
bottom.
was the bottom isotropic coordinate that we had.
Right. Yeah. Okay. But is that generic, or was that just the example?
Well, all the problem we've done there's a few there. There's other people now publishing with this technique, with not me around, and it seemed to be quite. What I've shown you with 2-3 examples seem to be quite what's happening in those hurricanes. Now, do we have the full picture? I'm not claiming that, but we certainly have a piece of the puzzle here. That those Vortex Rossby Waves play an important role in redistributing the angular momentum. Now, how they are forced, what exactly the mechanism is doing that? Well, there's a lot to see there. Yes, Peter?
Well, I guess that's kind of that last comment you made. That, so you have some cases where you're thinking of these waves as arising from instability,
Yeah.
But you mentioned other cases where there wasn't any instability.
No. Yeah.
So what do you see as the mechanism for?
Okay. Some case were on a stable mode. I think that's well understood. I think that's the one. The others was mode which has a critical line and which are excited. Now, how we excite them? I didn't show this example. In the 2D example, we've looked, I'll give you an example where you don't have unstable mode, is what we call quasi-mode. I'm not sure how much people are familiar, but it's used a lot in plasma physics. And essentially, it is, if you try to, okay, let's say you have the linear equation, you stochastically force them. If there's some shear in the basic state, in the wind, you can excite easily some modal structure called quasi-mode, which are quite easily excited. They are quite peak in frequency space, so they're not discontinuous continuous mode, okay? But they have a frequency which is quite well defined. They are damped, so you can see that they are damped, and as they're damping, they accelerate. They can accelerate the vortex. That's an example. So quasi-mode is another, and those modes that I've shown you, are they quasi-mode at the same time? That I could not say with affirmation. Let's say when we've done the same type of work on the ultra-tropospheric dynamic of the planetary wave, the quasi-mode came out naturally there. It's something which was proposed by Farrell and Rivet a few years ago, and clearly you see them at the tropopause. They are quite well peaked, very well defined, and they are damped and help to accelerate the jet as they are dampening. So that would be the best candidate for this.
Well, thank you very much. Really,
Okay.
really good talk.